piece of software for this, so hopefully it's the right option. All right, and that's the reason why we use OCaml in this module, right? It's a language designed specifically for this purpose. So you're going to learn essentially two things, right? One is, what do we mean by language processing? What do we want to, what is the objective of processing a language, right? Creating a language, designing a language, implementing a language. And also the other thing that you're going to learn is what are the right tools for doing that, right? There are classes of languages that are especially designed for this. One is OCaml. There's another one called Haskell. Has anyone heard of Haskell? Yeah, okay. So they were developed for this particular purpose. We're going to do this module. We're gonna do it by essentially going through a sequence of languages, a hierarchy of languages. We're going to start with a very simple one, and we're going to keep refining it and adding new features and new constructs to it, and we're going to develop it into a full-fledged programming language. And at each step, we're going to learn how to process the new stuff that we are adding to the language. Many of the constructs are relatively well known, right? So most of you are level 4, right? And some of you are even older than that, I'm expecting, right? So all of you have seen a couple of programming languages. You're seeing now yet a new one, right? You know the basic constructs of programming. You know what statements are, you know what procedures are, you probably know what modules are, exceptions, all the essential mechanisms of programming, right? So in terms of designing a language, we're not going to add a lot of new stuff. We're going to look at perspective of how to put things together, but not necessarily introduce a lot of new concepts. The new concepts are going to come in the way we deal with those at the level of implementing everything, right? We're going to look at how do we interpret a language, how do we compile a language, how do we statically analyze a language. And we're going to do this through, in the lectures, through a tool that is extremely abstract. It's called semantics, and it's going to just give you hints about how to write your code. Because this tool is extremely abstract, we can express things extremely well, right? We're going to introduce semantics rules, and you're going to see that in a couple of slides we can say quite a few things about a programming language. And that's going to be our universe of discourse for this module. So let us start with our first language, which we call EPL. The naming scheme is very simple. The PL stands for programming language, and the simplest form of a programming language is an expression, right? So this is going to be an expression programming language. It only has expressions. And this is the synopsis for today. We're going to talk about syntax, and then we're going to introduce the notion of semantics. There's two types of semantics here, dynamic and static, all right? And hopefully we get to go through both of them. And we're going to look at the concept of a virtual machine, which you might have encountered before. Where did you encounter it? JVM, right? So you know at least one language that has a virtual machine, which is called JVM. But you should know that most programming environments nowadays have a virtual machine. Even OCaml. OCaml has multiple targets, and it has as well its own virtual machine. So one possible compilation of OCaml is into bytecode, and the bytecode is interpreted by a virtual machine. Python, right, is compiled into a virtual machine code that is executed. That you have these PYC files, right, that result after Python execution. Those are files that can be executed by the Python virtual machine. And also JavaScript has a virtual machine inside every browser. All right. So we're going to look at that. It's a very central concept. It simplifies things for us a lot because it gives us an idea of what the target of a compiler is without having to talk about a processor, right? if we weren't compiling to a bytecode to a virtual machine, what would be our alternative? What does C compile into? Louder. Binary, right? What's that binary? Louder. Well, ones and zeros, but of course they're ones and zeros. Everything is ones and zeros, right? This image is ones and zeros, right? So what are those? What's that binary? What happens to the binary? What executes the binary? So we're typically typing the command, and the command executes, right? What happens to the binary? OS classes, computer organization classes, remember those? Right? So the binary is executed, is machine code, right? It's executed directly by the processor. Processors happen to be very complicated devices, and it would take us a lot more time to produce code for that, or explain how that is produced, and to explain the entire mechanism of taking the code and executing it. So the virtual machine is going to give us an abstraction of that, but we'll still retain the essential feature that the code gets translated. All right, it's very important to understand. So let's talk about syntax. The way we introduce everything and we talk about everything is via inductive rules. All right, and what you see now on the screen is an example of that. Inductive rules have two parts. There's a horizontal line. Above the horizontal line are the premises, and the underneath it's what follows from those premises, right? Sort of the conclusion or the outcome of that. All right. So we're saying if U1 and E2, for instance, taking the one in the middle, if U1 and E2 have some property, then so has whatever is underneath. All right? That's pretty much the type of reasoning that we're trying to introduce. Certain rules do not have a premise, and it means that whatever is below the line is a fact, right? It doesn't need any premise. It's unconditionally true, or it unconditionally satisfies whatever we try to define. So now let's before we go into the syntax of EPL, what is a language? And what is a programming language? We could ask what is a language in general, and then you're going to have a lot of definitions, right? But there's a very simple one, right, which would be the set of all strings that one would consider correct as part of the language, right? For a programming language, that's very easy, because typically we have a compiler or an interpreter. We take a string, we put it through the compiler. If we don't get a syntax error, that's part of the language. If we do get a syntax error, that's not part of the language, right? It's a very deterministic thing. It's decidable, right? So that set is well defined. It is infinite because we're not restricting the length of the strings, but it is decidable, right? We can say for sure which is part of the language and which is not, right? So we are trying to define a set of strings that represent correct expressions, okay? And we do that via inductive rules. And we're taking shortcuts in these inductive rules, right? So I'm going to look at the ones that have true and false there. And I'm going to say true is a correct expression unconditionally. There's nothing above. And false is a correct expression. Okay? So these are actually, they fulfill the definition of an inductive rule. They are really, truly inductive rules. The one at the left, the one that has n underneath, below the line, that's actually an inductive rule scheme. All right? It's not a single inductive rule there. We have a set of inductive rules. Right? In other words, we're saying that there's an infinity of rules saying that every single number is a correct expression. That n stands for an arbitrary number, right? And we can make that number vary from 0 to infinity, or from minus infinity to plus infinity. We're not going to be bothered by the fact that in computing, in general, ranges of integers are limited, right? We're just going to assume any possible value. And we're saying that there's an infinity of rules there. Any integer is an expression. And now comes the interesting aspect. And again, I'm going to look at the more interesting one, which is in the middle, E1 and E2. We're saying that if E1 is an expression and E2 is an expression, then whenever we put an operator between E1 and E2, all right, that's a correct expression. And again, we're taking sort of a shortcut. I'm just going to go to somewhere where there's a table. I'm sorry, we don't have the table here? Somewhere there is a table. Okay, here. All right. So these are possible values of p, right? The p that you see on the slides that I showed you previously, that is an operator. It's a binary operator. Okay. So I'm just going to go back there, and we're taking a shortcut. And let me explain what a shortcut is. We're essentially saying that E1 plus E2 is a valid expression, right? So this, you can think of it as equivalent to plus E1, E2, right? And then we can have minus, we can have star, we can have division, and so on, all the binary operators, right? So we're taking sort of a shortcut, and we're saying by this notation, right, that we're placing a binary operator between E1 and E2, and that's a valid expression. Okay? Now, a similar thing happens with unary operators, which we have here. All right? So we have negation and unary minus. And we're going to follow the example of OCaml, where unary minus is represented as a tilde. Right? Unary minus in OCaml is not the minus, the dash, but rather. So we're saying that if this E is a valid expression, then minus E is a valid expression, and negation E is also a valid expression. Is this clear? I have no way to turn this off. Is this clear? Is everything clear so far? So, from this point on, we're going to consider the writing of the writing 1 plus 2 and the writing plus 1, 2 as being equivalent. We're never going to make a distinction between them, right? Whenever you see this one, you can assume that actually this one is meant, right? This simplifies things for us every so often, all right? And that can be applied recursively. So if we take a look at this expression, it could be rewritten in this format. So this is sort of a prefix operator format, right? And the advantage of this is that it takes into account operator precedence. All right? So as soon as we have this expression, we're saying, oh, well, this star has higher priority, higher precedence as compared to the neighboring plus. All right? This is not apparent in the infix form. And this is an important aspect of syntax, but it's one that we don't want to be bothered to cover here. Right? So we're going to sweep it under the carpet. We're going to look at our expressions at the theoretical level, at the generic level in this format, because we don't have to worry about the priority of operations. Okay? I have to find a better solution here. All right, so these are examples of expressions, all right, and they follow the previous rule, right? So you see, 17 is an expression, and 20 is, 17 is an expression, right? Then we can say that 20 is an expression, and 4 is an expression. Therefore, 20 minus 4 is an expression. And we know from before that 17 was an expression. Therefore, 17 less than 20 minus 4 is an expression, right? And furthermore, right, 4 is an expression, and then 11 is an expression. Therefore, 4 plus 11 is an expression. And then 10 is an expression. Therefore, 10 equals 4 plus 11 is an expression. And then, if you look at this and, we know that what was on the left, we established that it was an expression. What is on the right, we established it as an expression. So the whole thing is an expression, right? Everything follows the inductive rules that we have previously established. Okay? So this is a neat way for us to define pretty much everything. So you're going to see a lot of concepts defined in this way throughout this module, right? So far, we are worrying only about syntax. All right? Questions so far? All fine? Cool. So you're going to tell me, you're going to ask me now, okay, this is fine, but if I am to write code that takes a string and gives me some data structure that represents the syntax of the expression, how do I do that, right? It's not very clear, right? And what we're going to say, and it's something that we don't want to be spending too much time on because it is a very sophisticated area in itself, right? So if we were to go into how to turn an expression into a data structure representing that expression, into its syntax tree, right, we would, that's a reasonably difficult topic to cover. It would require a lot of time, and then we wouldn't have time for other things that we find more interesting. But there's two concepts that you have to remember. It's lexical analysis and parsing. And the good news is actually that these two aspects of syntax analysis have been automated very a lot, right? There are very good automated tools for generating the a lexical analyzer and a parser for a language, right? And for most languages in widespread use, these tools already exist. It's very unlikely, if you want to do any language work, that you will have to write your own parser and your own lexer. All right? And for this reason, these topics are usually a bit set aside when we talk about languages and their semantics. Okay? So, just to go into it just a little bit, right? You see, 17 is an entity made up of 2 characters. It's a number, but it's an entity made up of 2 characters. Okay? And we want to treat it as a single entity. So we would take those characters and put them into a single element, right? So from a data structure perspective, right, 17 as 2 characters will fit into one object, right? Less than is a single character, but it's also a concept by itself. So less than will go as a single character into another object, right? So everything that has a standalone entity will become its own object, and we call these objects tokens, and this is what a lexer does. All right? If we go further and think in the wider context, we're going to see later identifiers, and these identifiers have a variable length, right? And an identifier is a standalone, has a standalone concept, is a standalone object. So all the characters belonging to that identifier will go into a single object. That's another token, right? You will have characters, you will have operators that are made up of multiple characters, like plus plus, right? Those will, or equal equal, right? Those will go in their own token as well. So this is the purpose, the objective of a tokenizer, of a lexer. All right, this is what you see here. Split the program string into a sequence of tokens. Now the parser will take the sequence of tokens and turn them into a tree. Okay? What would be the tree, for instance, for this expression? What's the root? Tell me. And, right? The ampersand sign. Let's go to the left. What's here? Less than. Very good. Then here, 17, right? Then here, minus. Okay? Okay? Equals. Okay? If I would ask you to take the expression into this tree, you would probably remember you've done it in data structures and algorithms, right? In the class called data structures and algorithms, right? So at this level it's not that complicated, but when you have a full language, things are a bit more complicated. But this is essentially what happens, right? Every program, if you think about it, has a hierarchy. It has scopes, and scopes are nested, and from the nesting of scopes we get a hierarchy, and that can be put into a tree. Parsing will take the string representing the program and turn it into the corresponding tree. All right, so at least at the conceptual level, it's relatively easy to understand what parsing means. Okay. If we were to represent the nodes of a tree, of this syntax tree, let's try to do a simple exercise. We try to represent the nodes of the tree, right, by some data structures. And we're going to try to do it in two different languages, in Java and in OCaml, right? And this goes to argue in favor of OCaml as being a better tool for performing language processing, right? So we would have expression as a public interface. Let's take the Java case first, right? So we would have expression as a public interface, right? And we will have several types of nodes because we have at least two types of entities, right? We have numbers, right? And we have operators. And with operators, we have binary and unary operators, and with actually we don't have just numbers, we have constants, and with constants we have Boolean constants and integers, right? So we would have a class called Boolean constant, implements expression, right? There's the string corresponding to that, okay? And it needs to have a constructor because this is what Java looks like. If we have a binary primitive application, right? Then again, the operator, the binary operator, the plus or the minus or the star, has to be stored inside. So it will be stored inside here, okay? Inside here, in the operator, right? And then we have two children. And the children are, we just saw the tree, right? Are expressions, right? Recursively. They're not just numbers, or because we can have any expression on the left and right side. All right, and we have to have a constructor because this is what Java looks like. Okay, so we would write at least three classes, but we still would have a class for integer constant, and we would still have a class for unary primitive application, right? This is all we have to write in OCaml, right? So every class of Java becomes a line in OCaml, right? So we're saying that there's one type of node called that is a Boolean constant. There's another type of node that is an integer constant. There's another type of node which is a unary primitive operation, and there's yet another type of node which is a binary primitive operation, right? So what do we have inside a Boolean constant? The Boolean itself, either true or false. Inside the integer constant, we have the constant value that we read from the expression. A unary primitive operation will have an operator identifier, all right, and another expression. So notice that as soon as we have operator applications, the argument is an expression, right? So it's a pair of operation identifier and an expression. And the binary primitive application would have an operator identifier and then a left expression and a right expression. Cool? Wonderful. So, OCaml is better. Questions so far? There's one important omission from this language. What is the omission? What do you typically have in expressions that we haven't mentioned here? No. So variables is another level of language. We're going to have variables. No? So let's say I write 1 plus 2 times 3. But I want the 1 plus 2 to be executed, to be evaluated before the star. Parentheses, right? Brackets. Why do you think we don't have them? Where did we hide them? Louder? Yes, so we said at some point that we're going to consider this form and this form perfectly interchangeable, right? But in this form, I could encode it in such a way that the plus here is evaluated before the star, right? So actually, I wasn't quite truthful when I said that they're completely interchangeable, right? I can say more things with this form than I can say with the other form, right? But this sort of relieves me from the obligation to provide parentheses, because I, at this point, can accept any kind of expressions, right? As long as I write them in this form, and I'm in no way limited. I think actually the parser that we have in the lab does handle parentheses, right? Yeah, okay. So what you have in the lab will be a full-fledged parser. But here we swept it under the carpet. Okay, let's talk about semantics. So we have this string, which we say comes from a programming language. And by itself doesn't mean anything, right? So we want to attach a meaning. Okay? If you think of the English language, you take sequences of symbols, right? And they mean stuff. You understand something from them, right? What could we understand from programming language? How could we go about saying that something has a meaning? It's actually very simple, right? I have on one side a set of strings, right? I'm going to put on the other side a set of meanings. What are the meanings? Objects that I put in that set, right? I'm going to pluck some objects from the universe, put them in the set, say this is my set of meanings. And I'm going to create a correspondence between the two sets, right? And I'm going to say this string means that object, okay? Now we can do this in many, many ways. We can put in this set of meanings anything we like, right? So one thing we can put is binary code. Another thing we can put, and we're going to do later, is sequences of virtual machine instructions, which when executed, do something that we would expect of that program, right? We already have an expectation of what the program means. We're just mathematically trying to match our conceptual expectation, the one that we have formed by learning the language, with something that is mathematically definable or has a real representation, right? But at the abstract level, we can be a little bit more abstract. We can put a set of mathematical objects in here, right? Not binary code, not concrete objects, just mathematical concepts. And that's the set of meanings, and we try to create a correspondence, right? So our set of meanings is going to vary. It's going to be different, right? So at this point, we're going to try to define the dynamic semantics of EPL. The dynamic semantics sort of tries to mimic the execution of a program. All right, so that's the ultimate goal. Of course, when we when we say execution, we are thinking of operations that are executed in sequence, right? So ultimately, the sequence of execution is going to be important, right? But at this point, we only have expressions. With expressions, it doesn't quite matter. Order is not that important, right? I can evaluate the left-hand side of an operator and then the right-hand side, or I can do the right-hand side first and then the left-hand side. I'm still going to get the same result, right? So the dynamic aspect is going to be really revealed a little bit later. All right? So what we want is to match every expression to a value. But think of that value as a mathematical object, right? So I have the number 3, which is made up of the character 3, and I have the mathematical value of 3. They are written in the same way on a piece of paper, but conceptually they're different objects. So can you understand the distinction? All right? It's kind of important to understand that. All right? So we're going to denote those values by V. Okay? We're going to denote those values by V. All right? And we're going to start with inductive rules, right? And we're going to say that in these inductive rules, we're going to define a new operator. It's not a programming operator. It's not a programming language operator, right? It's a relation. Actually, it's not an operator. I'm talking about this symbol here. And you're going to think of it, it's greater than, it's sort of an arrow. It's an arrow indexed by EPL, and we're going to call it evaluates. Right? Evaluates in one step. Okay? So we're going to say that whatever is on the left evaluates to whatever is on the right. Okay? Now, the primitive constructs of the language are operator applied to value. Right? Operator applied to value. I think actually there's a rule missing. I'm not entirely sure that the rule appears at some point. I promise to find a better solution to this clear screen thing. I like to annotate the screen, but I want to make sure that. Okay, so we're gonna have another rule, right? Saying that without any premise, a value evaluates to itself. But what's on the left and what's on the right? Think of the the number 3, which is the character 3 on one hand, and on the other hand we have the concept of the number 3, right? Which is a mathematical concept. But we're saying essentially that this relationship exists, right? So V as a single value evaluates to its mathematical interpretation, and that's something we cannot define. It is predefined. It comes predefined, right? It's a basic fact. The fact that 3 evaluates to itself, right? We cannot. We just accept that, right? So then, once we have that, we're going to have primitive rules, right? So we have an unary operator applied to a value, and we're going to get another value, right? And this is again, it's actually an inductive definition scheme, right? It's an infinity of rules, and they're essentially saying things like, right, negation of true evaluates to false. Right, so you think of all the instances of V1, V2, and you think of all the possible values for P1, right, which are essentially negation and minus. And all those instances, you can put them in a big table, and they're sort of givens, right? They're given to us. There's no way to compute that. We know it from up front. That's the definition of negation. That's the definition of unary minus. And in the case of binary operators, right, that's the definition of plus, minus, star, and, right? The fact that 1 plus 1 is 2, the value is to 2, that's part of the definition of plus. Right? We don't have a better definition, mathematically speaking. Does it make sense? So these are primitive rules. We don't have a more primitive way of defining. We can't define them in terms of anything else. So we just accept them. Is this clear? So, if that's the case, let's see how we can define rules for complex expressions. All right? So, what we saw in the previous slide was a one-step evaluation, right? We have a very simple expression, either the value itself or something that is 1 plus 2, and we say that it evaluates to 3 by definition, right? So that's a one-step evaluation. Now, we're going to have a we would call a contraction. So we will define our one-step evaluation, right? And think of that as when you were in primary school and you were learning to evaluate complex expressions, you would do what? You would perform one operation at a time. So you would write a long expression, and then you would copy almost that entire expression. You would only perform one operation inside, right? That was the next step. And then you would copy it almost identically. You would just perform another operation, right? So we're trying to define the relationship between each of the steps, and that is a one-step evaluation. Now, an example of one-step evaluation is the contraction. So we're just going to say that if E contracts to E prime, then E one-step evaluates to E prime. So now we have a new relation, the one that has this arrow with a stopper at the end, right? And indexed by APL, and we're saying that E one-step evaluates to E prime. You see, we're introducing names to each of the rules on the right side, right? So because this comes from the contraction rule, we call it contraction. Then we're going to say if E one-step evaluates to E prime, then operator applied to E one-step evaluates to operator applied to E prime. All right? Does it make sense? What does this mean? So it means that, let's say I have minus 1 plus 2, all right? So because 1 plus 2 one-step evaluates to 3, minus 1 plus 2 evaluates to minus 3. When I say minus 3, notice that I'm leaving a space between minus and 3. This is not a value of minus 3. This is operator minus applied to the value of 3. This is yet another expression. Okay? Similar we go for binary operators. So if E1 one-step evaluates to E1 prime, then notice that we are performing only an operation only on the left-hand side. Right? So this expression P E1 E2, which you could think of as E1 plus E2, if one-step evaluates to E1 prime plus E2. We're not bothering to perform two steps. You might be tempted to take this one and add it here and say that this is E prime. We don't bother to do that. Okay? All right. So finally, we can perform a one-step evaluation in the right-hand side of an operator. Is this clear? Yes? All fine? So as I was saying previously, the order is not that important right now. Right? We are completely non-deterministic. So in many cases, we will have the option of choosing either this rule or this rule. Okay? Yes?
Can I ask, for contraction, does contraction mean like that arrow operator or means?
So contraction is a conceptual prop, right? So if you think in terms of programming, you would define a small procedure that implements this, and then you define everything else in terms of that small procedure, right? So this small procedure represents the base case, and then here you have the recursive cases. All right. So then you would have essentially to distinguish between, right? You would look at, oh, is this a case of contraction or is it a case of something else? If it is a case of contraction, let me invoke the contraction procedure. If it is not, then I will have some recursion in there. So let me go and figure out the structure of the recursion and apply the recursion accordingly. Does it make sense? So yes.
You can give an example and then you then say which of the rule can apply. Maybe that's also interesting. Yeah, maybe just that example.
Let's take this example, right? So so let's evaluate it by step by step, right? So this one is obvious, right? So then we have 3 plus 2 times 20. 3 times 2 plus 20, right? So what applies here? And obviously we're going to assume this, right? So because 3 times 2 goes to 6, right? One step evaluates to 6. But how do we know that 3 times 2 one step evaluates to 6? So this would go to, let's draw the arrow, to 6 plus 20. But how do I do this? How do I know this? I know this because, and ignore the typewritten stuff, what we write above. I'm just going to go here, right? What do I write above the line? How did I make this judgment? That 3 times 2 plus 20, one step evaluates to 6 plus 20. It's because 3 times 2, one step evaluates to 6, right? How do I know this one? It's because 3 times 2 contracts to 6. And this is by the definition of star. I don't have any other thing to rely my reasoning on but the definition of multiplication. Does that make sense? Cool. Have to find a way to attach a so there's a script for that thing, a configuration script. I didn't bother to read it fully. So now what's a full evaluation? We have an expression that is very long and it evaluates to a single number, right? And we've already seen we're applying one step after another after another after another, right? And we're applying those steps until no step is further possible, right? So we're essentially building the reflexive transitive closure of the one-step evaluation relation. Does it make sense? Everybody knows what the reflexive and transitive closure of a relation is? Yes? No? No? So you have a graph, right? You can reach from A to B. So if you can reach from A to B and if you can reach from B to C, then you can reach from A to C, right? So if I compute the reachability relation in the graph, which point can I go to which other point? I have computed the reflexive and transitive closure of that graph, right? The relation, the basic relation is the arc, right? And the transitive closure is the path, right? Almost all relationships can be expressed as a graph. So the relation is the arc, and the transitive closure is the path. So what's important here to understand, right? That I can go from E1 to okay, so actually these rules are defining the transitive closure, right? So the transitive closure, which is typically denoted by a star, is the Kleene star. Kleene was a mathematician that explored that. Where do you see this star also? So that you make a connection. Where do you see something followed by a star? In coding. Yeah, pointer, but not. I'm not talking about pointers. When you search something, regular expression, right? So what does the star mean? Any number of repetitions of the including 0, right, of the previous expression, right? So this means any number of applications of the arrow, including none, right? So we're saying that if E1 one step evaluates to E2, then E1 reflexively and transitively evaluates, not self-evaluates, to E2 as well, right? Then if E1 evaluates to E2, right? So this is the path aspect in the graph. If E1 evaluates to E2 and E2 evaluates to E3, then E1 evaluates to E3. All right, and then E evaluates to itself always, without any premise, right? Why is the self-evaluation important? Because for instance 3 is a valid expression, right? What's the value of 3? Well, it's 3. How do I know? It's because it evaluates to 3 with 0 applications of the self-evaluation expression relationship, right? 3 evaluates to 3 with 0 applications of the. Clear, right? So we have defined semantics. This is the dynamic semantics. Sounds weird because there's nothing dynamic about it yet. When we extend this to a full-fledged programming language that has while loops, then it's going to become apparent why we call this dynamic, right? Because the sequence of execution of steps is going to be important there, and we're going to take that into account. Okay, but this is an example of dynamic. And look at what we've done. What we've done is we defined a mathematical relation, right? Which has a very strange symbol there. But never mind, it takes an expression and it gives you a meaning of it, right? And for this case, we're saying that the meaning of the expression is its value, right? You're going to say, oh, what's the big deal about this? Well, from a computer's perspective, that the expression is a string. The value is a completely different thing. You have to perform computation, right? If you think in terms of machine instructions, right? It's not quite obvious what machine instructions are going to put there to produce that expression, right? So it's important to formalize the fact that from this string we are going to this value and this is what we consider its meaning. Cool? Wonderful. So, how are we going to implement? We're going to have a procedure which we call the evaluate. So this would be the OCaml, the Java version, and warning here, it's not going to be, OCaml is not going to be much better, right? So you have to implement a test of reducibility. You have to look at the expression and say, oh, is there anything I can do to this? Is this already not something that is that has a value by definition? And if it does not have a value by definition, then we can apply to it the one-step relation, right? We're going to implement a function that performs one step. Otherwise, if it's irreducible, the expression is its own value and we can just return it. OCaml is gonna look the same, right? Looks a bit less verbose, still about 3 lines of code if you don't count the braces. By the way, this brace is typo, so treat it as such. Okay, next thing, static semantics. So we're going to actually follow pretty much the same structure of reasoning, but our set of meanings is going to be different. Our set of meanings is going to be types. In our expressions, we have 2 types. We have booleans and integers, right? And I would like to derive the type of that expression. If it's 1 plus 2 plus 3, the type should be integer. If it's 1 plus 2 less than 3 plus 4, the type should be boolean, right? And if it's 1 plus 2 less than 3 and 4 plus 5 is equal to 100, then the type is also boolean, right? It's not very obvious how that would happen, and therefore we have to go through a similar process, right? Importantly, certain expressions, even though they are syntactically correct, right, they do not have a type. True plus 1, we cannot assign a type to that, right? And you're going to say, if we type it in JavaScript, we do have a type for it, right? And that's very true, right? Because JavaScript is not a strongly typed language, right? So we're going to introduce a new concept soon, which is strongly typed languages, and we're going to argue that having only expressions that do have types in our programs is a very good thing. Cool. So true plus 1 doesn't have a type, and therefore we would like to exclude it from the set of programs that we want to accept. It is syntactically correct, all right, but it is not semantically correct, all right. So inside compilers, after parsing, there will always be a phase called semantic analysis, and the semantic analysis will try to detect this kind of anomalies, right, and reject programs that don't comply. We can do a lot more types. Semantic analysis is an area of research in itself, right? We're going to just scratch the surface here. But this is pretty much what OCaml is doing, right? You have noticed already that OCaml rejects expressions that do not have a type, right? There are many other languages that do the same. There are many other languages that don't reject it at the compile time, but they do reject it at runtime. Python, for instance, right? You can't add a integer and a boolean, though you're not going to get the error at compile time. You're going to get it at runtime only if that statement gets to execute, right? All right. So we're going to introduce a set of 2 meanings, integer and boolean, right? This is our semantic domain. So let's start introducing some terminology as well. So previously our semantic domain was the set of integers, because we were assuming that everything, actually not integers and booleans, right? I didn't give examples on booleans, but we could very well have boolean expressions. And we didn't give any mistyped expressions, right? So notice that what happens, so before we go into typing here, what happens here if we have a poorly typed expression? Let's say I have 1 plus true. What happens then? Louder?
The error will be covered.
Well, we're just talking math here. Don't worry about the compiler, right? So we're looking at the rules that we have set out. What happens with the rules? What can we do? So we have 1 plus true, and we want to perform one-step evaluation. Louder? I can't quite understand, sorry. There's no rule, right? So we're stuck. That's all that happens. It's a very unfortunate kind of thing, right? You're just stuck with that expression that doesn't make sense. It can be a very complicated expression. You're just stuck, right? There's no way to provide an error message. There's no way to tell you. The only thing that it can do out of these rules with a mistyped expression is to give it this incompletely evaluated expression and says, this is how far I got, right? This is what the formal mechanism here provides, right? Obviously, what's going to happen at the level of a program, if you implement this, is you're going to get some sort of an exception, right? So there's going to be some unhandled case, and some exception is going to occur naturally, which is not very good. So let's see how we detect the type. So the rules are in fact very simple. We have a semantic domain, right? We've went through these examples already. I talked about these examples. So let's talk about the rules, right? So we accept as a universal truth that true has type bool, false by definition, right? False has type bool. These are a lot easier to accept. Previously, you had this infinity of rules saying that 2 plus 3 is 5, 2 plus 4 is 6, right? We had one single schema that was is essentially reifying this infinity of rules. Here it's a lot easier, right? True is bool, false is bool, every integer is int, and then we go into the recursive cases. If E has type int, right, then P1E, so this rule right here, sorry, just I don't want to scribble again because I'm going to go through. So in front of here is a P1. P1E is int, right? As an example, I think this actually was tilde, and tilde in LaTeX sometimes is not printed. So I think this was tilde. So this is the unary minus. So unary minus E has type int, right? If E on the other hand has type bool, negation E is bool. Do you know LaTeX by any chance? I'm not sure if any. Yeah, really? Okay, that's cool. I think the world had outgrown it. Dr. Chen still uses LaTeX. I used to write my PhD thesis in LaTeX, but I hardly use it today. All right, so if E1 has type T1 and if E2 has type T2, P, binary operator applied to E1, E2, has type T, where type T can be derived from a table dependent on T1 and T2. Okay, and this is the table. And notice that we do not have rules for combinations of, for plus we don't have int bool or bool int or bool bool. Okay. Now, an interesting case would have been here to have overloading. Right? So in many languages, for instance, I can add 2 integers and I can add 2 strings. And when I add 2 strings, it means concatenation, right? So that's possible, and we could handle that, right? We could have 2 instances for plus, one that handles int and returns int, and the other one that handles string and returns string, right? That would have been very easy to add here. All right, and there comes, the definition that is a bit of a letdown. We're saying that E is well typed if there exists T such that the expression E has type T, right? So it still doesn't give us a handle on expressions that are mistyped. Whenever we are applying those rules, expressions that are mistyped, we simply get stuck with them, right? We don't get a type for them. But at least we know a very clear thing, that if we don't reach a point where we have a type for them, when we're stuck, we can yield an error and return the fact that they are not acceptable. So if we manage to complete the application of rules and derive a type for an expression, then fine, it does have that expression. If we get stuck along the way, then it doesn't have a type, right? It's not well typed. And we're only interested in programs that are, or expressions that are well typed. All right? So this is a derivation of a type. So this is the successive application of rules. What happens is that each of these rules is an instance of, each of these steps is an instance of a rule, right? So if you look at the 2, there's nothing above the bar, but this is an instance of n being an integer, right? And also for 3 is the same thing, right? 3 is an integer because it's just an n. Now if you look at this, right? So all right, I'm going to draw with all the misgivings of the drawing system. If I look at this, right? This is an instance of the prim t rule, right? So 2 has type int, 3 has type int. Therefore, 2 times 3, according to the table, has type int. Now 7 has type int here, and this is an instance of the primitive rule. And then we can look at this as an instance of a rule, and 2 times 3 already established that has int, type int. 7 already established that has type int. So 2 times 3 greater than 7 must have type bool. All right? So we can build this tree-like structure where on every level we have instances of the rules, and this is what we call a type derivation or a type proof. We're essentially proving mathematically that 2 times 3 greater than 7 has type bool. Okay? Clear? And this is essentially very simple. So for the implementation, again, we're going to have a system of recursive procedures. All right. What we do is essentially compute bottom up. We start from the simplest elements in the expression. We attach type to them, and then slowly we build up to the top level where we have the full expression. Okay. So all these inductive rules, they give us an idea on how to go about implementing what we have. Now, type safety is a property which gives us some advantages. All right. So whenever we have a program that is type safe, what doesn't happen with it? And think of, obviously you're thinking of programming languages nowadays that connect to the web and call a RESTful interface and write to some files, and so there's plenty of opportunities to get exceptions from there, right? But think of a program that works in isolation. So starts from some input values that it reads from the keyboard and keeps crunching some numbers and outputs some other value, some result, right? So what doesn't happen with a program that is type safe? In a language that is type safe, what is guaranteed? That kind of a program will never throw an exception, right? Because if I don't do any file input output, I don't do any network, right? The only source of an exception, if you think of a language like JavaScript or Python, right, would be from mistyped operations, right? So you would add a number with a string, boom, exception. You would try to compare or try to perform the wrong conversion, or try to call, it goes even further. Once you introduce records, you could try to access a record, a component in a record, and the component doesn't exist. right? You say object.field, and field doesn't exist in the object, right? So this is something that type safety would prevent you from doing. That would not be a well-typed program. So if you have a type-safe language, that kind of exception can never occur. But it can very well occur in JavaScript or Python that are not type-safe. Is that clear? All right. So how do we ensure type safety? Well, it is based on two important properties, which I should have made this slide a little bit better. They're called progress and preservation, and we have them both in the expression language. And it's a lot more difficult when you have a language. So there are languages that are type safe, but they don't enjoy the properties of progress and preservation, and they would raise problems. And actually, most of the interesting languages don't have these properties. So what's progress? Progress means that you can always go ahead, right? If it's well typed, you can always perform the next operation. The next operation is going to be between operands that are of compatible types. So there's no reason to not be able to perform it, right? You have progress. And type preservation means exactly what we are expressing in our rules, right? So we created a formula list for defining the static semantics that actually ensures by construction preservation. If this has the correct type and this has the correct type, and these two types mix well with the operator that is below them, that is between them, then we get a correct type. Right? This is what we're saying here. We're saying that if this has a type, and this has a type, and this P is between compatible types, then we get a type. So this is preservation, right? The safety of E1 and E2 is preserved through P, through plus or minus. So this is what preservation means. Anyway, some technicalities about going about a proof. Is this more or less clear?
What about typecasting?
So typecasting relies on the property of or the feature of the language which is called subtyping, right? So where do you use casting? You have, let's say you're in Java, you have two classes, A and B. B is a subclass of A, right? So at some point in a procedure, you receive an object of type A, but you know for sure that it's of type B, right? So then you cast it into type B, and that works, right? If it doesn't work, then it throws an exception, right? And you can always perform safe casting in languages. So Java doesn't have that property really, but in a language like Scala, for instance, you can always ensure that the casting is safe. All right, but by saying that B is a subclass of A, what you're saying is that B is a subtype of A. It's like sort of it's a subset. Just the types are a bit different. By the way, so since we're sort of in the middle, let's break with a story. Let's have a story break. So how did types come about? The concept of types. Anybody knows? Who was the first guy who said, "Oh, sets are not good anymore. Let's try types"? So previously we had sets, right? And we still have sets. There is something called naive set theory, right? And you might have one. Have you heard of naive set theory? No? You have heard of set theory, right? So the one that you have learned, it's the naive set theory, right? The reason for that is that it has a paradox. Paradoxes in logic are not good. They produce contradictory theories where you can't be sure that something is true, right? And the concept of type was introduced to replace the one of set. And I'm going to give you the paradox, which is called the Russell's paradox. So Bertrand Russell, a British mathematician, found this paradox and also tried to replace it with a theory of types, which was the first one and which was wrong, by the way. So he couldn't get it right, but he is still known for the paradox that proved that sets as concepts are not good enough. So, have you heard of sets that contain themselves? Is it okay for a set to contain itself? Yeah, so some say yes. How many of you think that yes, it's okay for a set to contain itself? Can you give me an example of a set that contains itself? How about the set of objects that can be described in less than 1,000 words, English words? So the set of all objects that can be described in less than 1,000 words. I just said less than 1,000 words, right? So the set that I have just described contains itself, right? No? The set of all objects that can be described in less than 1,000 words. What I just said is less than 1,000 words. The set that I have just described fits into its own description so that it contains itself, right? The set of all objects in the universe. Well, that set is part of the universe, so it contains itself, right? So we have two types of sets. Sets that contain themselves, and obviously sets that don't contain themselves, right? So the universe of all sets in the world must be partitionable. I should be able to partition into sets that contain themselves and sets that don't. So the sets, I'm going to denote by A, the sets that contain themselves. Okay, so A is the set of objects X such that that don't contain themselves. Let's put it that way. X do not contain X. And by B, this is gonna be the set of objects X, or maybe Y. Doesn't matter what I put here. Y contains Y. Right? So now, does B contain itself or not? What do you think? So every set in this universe either contains itself or it doesn't contain itself. B is a set in this universe, right? So it either contains itself or it doesn't. Which do you think it is? So it's B, right? So let's assume that B does contain itself. This implies B contains itself, right? Let's assume that B, okay, let me start with B doesn't contain itself, right? So let's assume that B doesn't contain itself, then it fits this description. Then it must be the case that B belongs to A, right? Was it A or was it B? So should be A, yes. So where is A? Sorry, where is A? Does A contain itself or it doesn't, right? So A, right, let's assume that it contains itself, right?
So if we assume anything, we will imply the other one.
We will imply the other one. So A, let me assume that A contains itself, so it fits this description, right? So it must be that A belongs to B. But A and B are disjoint, right? So if it belongs to B, it cannot belong to A. right? If I assume that A does not belong to A,
Then we get that A belongs to
it fits this description, right? A belongs to A. So we actually can't know whether A belongs to itself or it doesn't. This is a paradox. Okay? And this is why naive set theory is essentially contradictory and wrong, and this is why the notion of types came along. Okay? In mathematics, and especially in the mathematics of programming and lambda calculus, people have developed very sophisticated type systems, which express a lot more than just allowing logic to be consistent, right? So when a logic doesn't have paradoxes, then we call it consistent. Is this cool? Types. So in the end, types in programming came to be, well, it depends where you look at, right? So if you look at languages like Java, types are relatively well-behaved concepts. They're not very sophisticated. But if you look at languages like Haskell, it's a completely different story, right? Types are extremely sophisticated and unwieldy objects that can express a lot of interesting properties, and coders use them for precisely that. Okay, break over. So let's try to clear the screen. Clear screen. And let's talk about the virtual machine. Now, we looked at the language of expressions. Now, the virtual machine is something that we kind of have an intuition about, right? It's not a completely foreign object. But if we want to define it mathematically, right? What do we see firsthand about a virtual machine? Have you thought about that? We essentially see its language. So there's a language that the virtual machine can execute. It is made up of instructions, and each instruction is extremely simple, does a very simple and well-defined thing, right? Because that's a language, we have to go again through the hoops of defining a language. We've done it with expressions. We have to do it again for the language. So part of our definition of the virtual machine is going to be a language for the virtual machine, right? We want to have some intuition of how instructions are executed. And then what do you think we're going to provide for the instructions of the virtual machine, for the language of the virtual machine? How are we going to say how every instruction is executed? So think of the concepts that we have already learned. We've learned two concepts, dynamic semantics and static semantics, right? Which of them do you think would be useful to tell us dynamic semantics, right? So we're going to define a semantics, a dynamic semantics, for the execution of the instructions, right? That's going to be our. So we're going to have another set of inductive rules saying, oh, this instruction executes in that way, right? And then we're going to define the translation between the expressions that we had initially and the equivalent virtual machine program that would evaluate to that, right? So we essentially were going to experience compilation, right? But think of the sequence of instructions, of virtual machine instructions that evaluate an expression. Think of it as just another kind of semantics, because it's an object, and semantics is a set of meanings, and those meanings can be anything, right? Specifically, they can be sequences of machine instructions. So compilation, the process of compilation, is actually a process of defining semantics, a form of semantics for our source language, right? That's the source language. The expression language is the source. So we're going to define syntax, all right? Via inductive rules. So the word done is a valid program, virtual machine program. And I'm going to tell you what each instruction means, so you're not left in the dark, because you're going to see these sequences of strange characters. You're going to see LDCI and you're going to wonder what the heck is that, right? So I'm going to tell you what it is. But my telling you what it is does not define the meaning. It's like a hush-hush kind of piece of information that comes into your left ear, right? So done is done, right? And done, a program made up of the word done, is a valid program. Then if S is a valid program, by prepending to it, right, then prepending becomes a very useful tool now, because done is always at the end, right? We're forced to finish with done, and we're just putting things in front of it, so we're ensuring that every program ends with done. So by prepending to it those characters, LDCI, and then integer, that's a valid program. LDCI means load constant integer. And the virtual machine has a stack. And you may remember from back in the day when you were doing computer organization, every processor has a stack, right? So our virtual machine is going to have a stack, and this will push the integer I on that stack. Does just that, right? LDCB is the same for booleans, right? The small b is going to be a boolean, and we're loading constant boolean by pushing it into the stack. So if we execute in sequence LDCI1 and then LDCB true, our stack is going to contain in order true then 1, right? It's last in, first out. All right. So now there's an interesting operation. We have plus. Plus doesn't have any arguments. Where do you think the arguments are? Because obviously it's the word plus, so it must perform some form of addition. Where are the arguments? In the stack. Some of you already know how the JVM works, right? Because this is actually modeling the JVM. So plus will look for the arguments in the stack. We'll pop 2 of them out. We'll perform the addition. We'll push back the result. So we're going to have a virtual machine whose final result is always at the top of the stack. All the operations are, all the binary operations are popping 2 elements, performing the operation, pushing back. All the unary ones are popping 1 element, performing the operation, pushing back the result, right? And how do we deal with constants? We push them directly into the stack, right? So we're going to have plus, minus, times, div. All of them have no arguments directly into the instruction, because the arguments are going to be found on the stack. And hopefully LT, GT, EQ are obvious, less than, greater than EQ. And you can have all the variants, less than or equal, greater than or equal, and so on. Whether we have them or not is not so important. Okay? So this sequence of instructions, which appears as a OCaml list, right, is a valid program. And by the way, so in the previous definitions, the dot means concatenation, essentially. So we have the word plus followed by the sequence S, right? That's what that dot means. And I don't think that's an OCaml operator. If I remember correctly, PHP has dot as an append operator, right? So this is a valid program. Now we're going to define a compiler, right? So we're going to take an interesting approach here, right? We haven't defined what each instruction means formally, right? We haven't done that. We sort of know informally what it means. So now we're going to define the compiler, and in that process, we're going to understand the compilation, and we're going to be satisfied that the compilation is correct because of our informal understanding of what the instructions are doing, right? But what would be a strong formal result at the end? To prove mathematically, right, that the execution of the virtual machine code produces the dynamic semantics value of the expression, right? So this is a process that we can handle mathematically fully, right? Everything is mathematically defined quite thoroughly, so it's a process that we can perform. What is the missing piece? What's going to be the missing piece? The missing piece is going to be the semantics of the instructions, right? So I have the compilation, I have the dynamic semantics of the expression, I need a notion of semantics for my virtual machine code, right? At that point, I can say what the execution of virtual machine code is, and I can establish the equivalence, right? And at that point, if I can say that for any possible language, any possible program, any possible expression, the execution of the corresponding compiled code is equal to the dynamic semantics, that's a very strong theoretical result, right? So we're going to try to go into that direction. I'm not sure whether I'm going to be able to finish, but we'll just go as far as we can, and we'll finish next time. So let's look at the compilation. Every constant, every occurrence of a constant in an expression. So what we have now is this curly arrow, and it says that the left-hand side compiles to the right-hand side. So if I have an expression that is an integer, its compilation is going to be the instruction that pushes that integer on the stack, right? And the same for true and the same for false. Constants are straight away pushed on the stack. Now, if I have an expression whose compilation is S1 and another expression whose compilation is S2, E1 plus E2 is going to be compiled into S1 followed by S2 followed by plus. And that makes perfect sense, because if we think from this perspective that the result of an expression should be always at the top of the stack, right? Then if E1 is correctly compiled, the execution of S1 will put its result at the top of the stack, right? If then we follow it by the execution of S2, so we execute from left to right. We execute S1, the result of E1 is at the top of the stack. We execute S2, the result of E2 is at the top of the stack. And what's on top of it? E1, right? And now I execute plus. So the two numbers come out, get added together, pushed back, the result pushed back, and what happens with this entire expression, S1, S2 plus? The entire result of it is at the top of the stack. So this is an invariant that we are preserving, right? Every compilation, every compiled fragment ensures that, right? Ensures the fact that its result is at the top of the stack. So from this you can see that the compilation is correct. So there's one trick here that we have to apply. Where's the done? The done is what is going to tell us when the program is finished, right? So we have to again employ a little prop. Oh, this is the prop. If E compiles to S, and we're going to call the curly brace fragment compiles. If E, the curly arrow, fragment compiles to S, right, then E completely compiles to S.done. What's the role of done? The role of done is to establish the fact that whatever is at the top of the stack is the final result of the computation. Okay? So this is again a little prop that ensures that everything finishes, right? We have this recursive constructs, right? But at the end we have to add a done. Okay? So this was actually the first rule that we introduced, and at that point it was probably very weird, but now if we present them in the reverse order, it's a bit it makes a little bit more sense. Is this clear? Does that make sense? So let's see an example. So I have 1 plus 2 times 3, right? So this compiles into LDCI 1, LDCI 2 plus LDCI 3 times done, right? And it's very clear now that if we execute the instructions in order, so this one is going to put 1 on the stack, then we have 2, then plus is going to extract 1 and 2 and put back 3, then we're going to add 3, then we're going to take, so now what do we have at this point on the stack, right? Once after we push this 3, we're going to have 2 3s on the stack, right? And then when we do times, we're going to pop them out, obtain 9 and push it back, right? Is it clear how 1 plus 2 times 3 becomes that sequence? Let's try to make sure we understand that, right? So I'm going to start bottom up, sort of, though normally I should start top down, but it's just easier to write. So we're maintaining that 1 plus 2 times 3 curly compiles, right, to this thing. I'm not going to write it because it's too much of it, right? So I'm just going to say this here, right? So why is this? Because 1 plus 2 curly compiles to LDCI 1, LDCI 2, and plus. And then and then a 3 compiles to LDCI 3, right? And then from this and this, I'm going to obtain exactly this, right? How do I obtain this one? Well, 1 compiles to LDCI 1, 2 compiles to LDCI 2, right? So 1 plus 2 should compile to whatever the left, whatever the right, and the plus, right? So this is how we obtain. So I can build again, as for the case when we had the types, I can build a backward tree, right? Obtaining at every level the compilation for every sub-expression. And all these compilations can be combined together by just concatenation. Does it make sense? Some of you look quite lost. So hopefully you can watch the recording and it will make more sense. Okay. Okay. Is it okay? Are there any questions? Yes.
And then at the other side is 3 and compounds 2, which is.
So 3 compiles to 3, and when I have a left side, which is 1 plus 2, right? And I already know the compilation of it.
Okay.
And
so
then
at the bottom, where would the times come in?
right at the end,
So would it
after
need
the
to
3.
be- Right, but would it need to be an expression at the bottom?
What do you mean by an expression?
Like what is it with 1 plus 2 would be compounding to 1 2 plus, right? And why would it not be that an expression say E 3 and compounds to equals 3?
So 3 compiles to 3. Right, 3 compiles to 3 from here.
Right.
I surely need better ways of writing on the screen. Let's do a quick one on the whiteboard. So 1 plus 2 times 3, and we're putting these in brackets, right? So 1 compiles to, yeah, so this is a curly arrow. 1 compiles to LDCI 1, right? And then 2 compiles to LDCI2. 1 plus 2 compiles to whatever. So this is the left side, this is the right side. So I'm going to copy this CI1. I'm going to copy this LDCI, LDCI2, and I'm going to put the plus, right? Is this clear? Now I have times 3. So 3 compiles to LDCI3, right? So I'm going to draw the line. Right? And draw the line. And 1 plus 2 times 3 compiles to whatever I've written here. So I'm going to call this sharp, right? So the sharp expression. And then whatever I've written here, LDCI3, and then the star, which is mult. Is it mult or what? Times. Okay? Okay? So now, so this was the example. Okay, so we have a language for the virtual machine. What's the semantics of that language? And you're thinking, oh, I know how to execute it. I put them in the stack, I pop them from the stack, right? Not good enough. We have to formally define it, right? So how do we define the semantics of this, right? So now we're getting into a real dynamic semantics, right? We want to take a program and defines what it means to execute it. Okay? So what else did a processor have? So we established that it has a stack, right? In the olden days of computer architecture, what else did a processor have? Important. Program counter, right? You're seeing the PC there, so that gives it away. So the program counter tells you what is the current instruction about to be executed. All right? So we need a program counter. So mathematically, this program counter is going to be a number, right? And so we have the program counter and the stack. So mathematically, what's a stack? It's a sequence, right? We're going to use it as a sort of a list, a sequence. We know what a sequence is mathematically, right? And we're going to put them together into a pair, because this is the only way of aggregation in mathematics, right? So our machine state is going to be represented by a pair, where one element is going to be the program counter, and the other one is going to be the stack. Okay? So we're going to have a transition function, right? We're going to say that if the current instruction, so we're going to, S represents the program, right? And S is sort of an array, a list, a sequence, an array. But whatever is in a sequence, we know which is the ith element, right? So S applied to index PC, right? Or the PCth element, right? SPC, let's say it's LDCI I, right? So we're saying if the current instruction is LDCI I, right? Then what does it mean that we execute? So what we define as execution is the one-step transition. We're transitioning from this step to this step. And this step is defined as the state of the machine, which, as I was saying, is the stack, OS, operand stack, and the program counter. And then if the LDCI instruction is the current one about to be executed, then we have to transition from OS PC to I prepended to OS and PC plus 1, right? So we have executed the instruction, so we have to move on with the program counter. And the result of that is the instruction is putting its operand on the stack. Is this clear? right? So we're defining the one-step transition. We're saying, if this is my instruction, from this old state we go to this new state. Okay? Similarly for a Boolean, right? So if my instruction is LDCB, then from OS PC I go to B prepended to OS and PC plus 1. Clear? If my current instruction is plus, so if it is plus, I need to have at least 2 operands in the stack, on the stack, right? If I don't, it's a cause for crash and burn. So if my current instruction is a plus, from the state I2, I1 prepended to OS and program counter PC, we move on to a state where we have performed the operation I1 plus I2. So we extracted I1 and I2, we popped them. We performed the operation I1 plus I2. That result, we push it on the stack. So that is now prepended to OS. And we have PC plus 1, right? We moved on to the next instruction. Cool? And that's pretty much it. This is the execution. So plus, mult, all the other ones, they're going to be very similar, right? If we have unary operators, we're going to have just one extraction, one pop instead of 2. And what happens when we do done? When we get done, right, we stop. We cannot go any further. And the result of the entire computation is whatever we find at the top of the stack. So we're going to say that the result of the machine is the value V if we have reached a point where the stack is, we have reached a point, we started from a point where the stack was empty and the program counter was 0, and by multiple one-step transitions, we have reached a point where the value V is at the top of the stack, right? And PC indexes the instruction done. Clear? So that's the result of the machine. So we let the machine execute, and whenever it's done, whatever is top of the stack, that's the result of the machine. Okay? And we would like to prove that, let's go through some examples first. Okay? So we have a sequence of instructions, and we can go through these transitions, right? So starting from stack empty and instruction counter 0 or program counter 0, we go to a state where we have 10 at the top of the stack. So the instruction is LDCI 10, and we're on the first instruction, so we're here, right? We start counting from 0. So this is the 0th instruction. Then we have the first instruction here, right? Then at that point, we have 10 at the top of the stack, right? We load 20, so we have 20 and 10, and we index instruction 2. Then we perform the plus, meaning that we pop 20 and 10, perform the plus, perform the addition, push back the result. We have 30 and 3. Then we push the 6, all right? And we have 6, 30, and we're at instruction 4. Finally, we pop the 2 elements at the top of the stack, perform the result, push back. So we end up with 180 and 5, right? And at that point, 5 is the index of done. The machine stops. The result of the computation is 180. Cool? Very good. So, how are we going to implement this? All right, so some instructions, some machines have registers, but we don't have registers here, so ignore that. So for execution, we're going to use a large switch statement, right? And that switch statement is going to discriminate between the various types of instructions, right? Your current instruction is either a plus or a minus or an LDCI or an LDCB. So we have a big switch, and we're going to say case plus, do this, case minus, do this, right? In all cases, you're going to advance the PC by 1, right? And in most cases, right, you're going to extract either 1 or 2 operands, perform an operation, and push back a result. There's a skeleton of implementation in Java, all right, which again shows the verbosity of Java. I'm not going to insist too much, right? For OCaml, we are going to have to represent the instruction as a type, right? So this would be what an EVML instruction looks like, right? So the opcode is LDCI. We call this an opcode, right? And it typically has an argument. So LDCI does happen to have an argument, which is an integer. LDCB has an argument which I'm not quite sure why, but this is code extracted from your labs. So this could have been a Boolean, but it so happens that it was implemented as an integer. Not quite sure why. And we have a variety of binary operators. Each of them have single words, right? And then once we have this, we can pattern match. So the equivalent of switch statement in OCaml is a pattern match. So we're going to say match C, and then for everything you're going to have a big match. More about this in the lab. All right, and I've already not given you a break, and it's 10 minutes to 9, so I think I'm going to stop here. I'm going to do this part next time. It's fun to do. It's interesting. I don't want to show it to you at the point where you're completely tired. It's actually an interesting aspect to understand about compilation, right? So please remind me next time to start with this, okay? If you want to think about what's here, can a compiler compile itself? Do you know compilers that compile themselves? That's not a cross-compiler. A cross-compiler is, for instance, you write an app on your PC and you install it in your phone. That's a cross-compiler. It's a process called bootstrapping, right? So the very first version of a compiler has to be written in a completely different language, right? I'm coming up with this completely new language that nobody has heard of, right? The first version of that compiler I have to write in a different language. Okay? Now I have one compiler for that my new language. Can I write the next version of the compiler for my language in that language itself? Of course, what's to stop me? So what's going to happen next? I'm going to compile the new version of the compiler with the old version of the compiler, right? But the new version of the compiler has goodies, has all sorts of improvement, right? So what am I going to do then? I have a binary of my new version of the compiler, and I have the sources of my new version of the compiler. So I'm going to apply the new compiler to itself and get a better version of that very same compiler, right? That's called bootstrapping. So a compiler can compile itself. We're going to talk about this next time, right? So there's this very interesting diagrams that show a little bit of the relationships between languages, interpreters, and compilers, right? So just to be aware of what we've done today, the dynamic semantics defines an interpreter. And we're going to keep defining dynamic semantics for our languages, and that's what is called typically interpretation, right? Then with the virtual machine, we have defined compilation, right? And then the interesting thing is that, yes, the expression is compiled into virtual machine language, but the virtual machine language is interpreted by the virtual machine. Okay? Okay, next time. All right, thanks for coming. See you next time. If you have any questions. So I have an email in the department. It's razvan@comp, right? I have an email with Facebook, which is razvanvoicu@fb.com. I will be more responsive typically on the Facebook one. If you have dying needs to contact me, please use the one that it's also easier for me to access. See you next time.